In the previous lessons, we talked a lot about the wave function and how it can be used to extract all the information you can know about the system it describes. So it sounds like a pretty good thing to have access to, but how do we actually solve for the wave function? We get the wave function by solving the Schrödinger equation. We'll begin solving for the wave function by making a very important assumption. We first assume the potential does not depend on time. This time-independent potential allows us to solve this differential equation by using the separation of variables technique. Using this approach, we choose the variables small psi and phi to represent the separation of the respective space and time variables. We then substitute these two functions in place of the full wave function in the Schrödinger equation. We can begin to separate the variables onto different sides of the equation. After some algebra, the Schrödinger equation is separated with the space variables on one side and the time variables on the other side. Since one side depends only on space and the other only on time, changes in one of the variables on one side will not affect the other. Thus, each side remains constant to changes in the other. We can now break the differential equation into two parts and set each part equal to a constant. First, for compactness, we'll execute the derivatives on the two time and space functions. In the form shown here, each linear term has the units of energy, thus the constant must have units of energy. We choose the separation constant E to symbolize the energy that each side of the Schrödinger equation represents. When the variables are successfully separated, phi and psi can be solved for. Solving for the time-dependent phi yields a negative complex exponential. Solving for the other side of the Schrödinger equation is a little more difficult because in order to solve this side of the Schrödinger equation, a potential must be first specified. Furthermore, if we rearrange the time-independent side of the Schrödinger equation, we now have what's referred to as the time-independent Schrödinger equation. Again, given the specified potential that the system described by the wave function is in, we can solve for the time-independent wave function. We can then combine this variable with the time-dependent variable phi that we solved for during the separation of variables process. The combination is what creates the full time-dependent wave function. A wave function describing a system in a time-independent potential has some very useful properties, but we'll cover them in the next lesson. But for now, let's review what we just covered. To get the wave function, you must solve the Schrödinger equation. In the first wave of lessons, we'll assume the wave function describes a system in a time-independent potential. This allows us to use the separation of variables technique and a known potential to solve the Schrödinger equation for the wave function. The separation of variables technique breaks the Schrödinger equation into two parts, but equal to the separation constant E for energy. Upon solving the two functions, the full time-dependent wave function has the same general form for a time-independent potential as shown here. That's the introduction to the process of the separation of variables for the Schrödinger equation in quantum mechanics for time-independent potential. I look forward to seeing you in the next lesson.